Welcome to the Alma webinar. My name is Vicky Denton, and I'm your moderator for today. Today's webinar is brought to you by the Asian Lubricant Manufacturers Union. Alma represents the combined interests of Asian lubricant manufacturers and provides services to help members grow their businesses. Before we introduce our guest speaker, we'd like to conduct a poll relating to this webinar. Are you or your organization involved with lubricants for electric vehicles? If so, in what way? Studying, planning what to do? In development of actual products or services for electric vehicles? Already offer products or other services customized for electric vehicles? Or no involvement as of yet? 26% said they plan or are studying what to do. 15% say they already offer products or other services customized for electric vehicles. And 10% are in development of actual products or services for electric vehicles. Our next poll is, when do you believe that the market for electric car lubricants will become large enough to warrant custom products? A, it is big enough already. Within 5 years, by 2025. Within 10 years, by 2030. More than 15 years away, after 2035. So the reply is still changing. I'll give you the results in a few minutes. Okay, 42% say within 5 years, that is 2025. 38% said within 10 years, by 2030. And 19% say more than 15 years away, that is after 2035. And 0% said it's big enough already. So that's great. So we can get started. So the topic of today's webinar is on electric vehicles. And our speaker is Zakarian. He's the owner and principal consultant of JAZTec Consulting. Jack spent 37 years at Chevron, most recently as Global Technology Manager for Driveline Products. We'd like to welcome Jack today. This is the third in a series of Jack's webinar. Good morning, Jack.
Good morning, Vicky. Can you hear me okay?
Yes.
Okay, great. And good morning to everybody else who's joining in today. I thank you for your time and attention. It's actually the evening the day before where I am in California. Actually, I'm in Oregon right now, but same time zone. So I was very interested to see the polling numbers. I think if we look at who has no involvement yet with e-vehicle lubricants and who's studying what to do, that's almost 3 out of 4 of the audience. That's nothing to be worried about. I think you'll find during this seminar that certainly electric vehicles are coming. I think it will still be a while. In fact, the other interesting poll said that none of you think that the market is large enough now. And it will take quite a while for a robust market to develop in electric vehicle fluids. So let's get started and let's see what's involved with lubricants for electric vehicles. So we'll talk about some terminology so you can understand the differences between different types of electric vehicles. We'll talk about the impact of these vehicles on both the manufacture of lubricants and the demand. Then we'll look at the performance properties that are needed for electric vehicle lubricants compared to regular conventional lubricants. And finally, we'll just touch briefly on sales opportunities for what we'll call EV fluids. At this point, and when the market is larger, the service fill will still be fairly limited. Most of these vehicles will be able to go quite a long time uh, with the types of fluids that will be supplied. And so one other channel to look at is also looking at OEM supply relationships. The first definition is what we call the ICE, internal combustion engine, and that essentially refers to the vehicles that we're all familiar with now, either gasoline or diesel powered. A hybrid vehicle is one that has both an internal combustion engine and one or more electric motors, and the motors are supplied with battery power. Uh, One of the things that makes hybrids complicated is there are a lot of options. Uh, the simplest one is what's called a micro hybrid, and that uses the same kind of battery that is commonly found on regular gasoline vehicles now, just a 12-volt simple battery. It doesn't use a lot of electric power, and essentially it will just help you with start-stop of your engine and what we call regenerative braking, so that when you put on your brakes in a car, as your car is slowing down, instead of just generating heat from all that friction, you're actually using the vehicle to essentially run the generator in the vehicle in the reverse direction, or the motor, which generates electricity. So whenever you step on the brakes, you can generate some electricity that helps keep the battery charged. A mild hybrid, which there are a fair number on the market now, it has the stop-start, regenerative braking, and also can give what we call a limited torque boost, which means that if you need to pass or accelerate or do something that just requires momentary boost from an electric motor, we can add that. That also doesn't use a lot of power. It can use a 48-volt battery, which very soon most vehicles will come with 48-volt batteries. That'll be the next step up, because even on conventional cars now, there's so many electronic gadgets and electronic controls that automakers are finding that we really need more voltage to keep everything running on today's vehicles. A full hybrid is something that will do everything I've mentioned already, but it also has the ability to run on the battery alone. And that takes an even larger battery, as you might imagine. But with the full hybrid, that still does not have the ability to essentially plug in and recharge the battery from an external power source. On a full hybrid, you still need to somehow use your gasoline engine to essentially provide power to recharge the battery. The final type, and the most versatile and really the best of the hybrid features, is what we call the plug-in hybrid. And that will do everything I mentioned, but in addition, you actually have an electric plug, which you can charge up your car while you're at work, or you can charge it in the evening when you get home. And in that case, you have a much larger battery. And obviously, the plug-in hybrid would cost a lot more than a micro hybrid. You definitely save a lot more CO2 and you get a lot more benefit, but you also pay for that with the higher cost. So finally, we have what's sometimes called a BEV, or just a full electric vehicle. And that's a vehicle that does not have an internal combustion engine along with the motors. It's just strictly a battery electric vehicle. So the Nissan Leaf, the Tesla vehicles, those would be good examples of full electric vehicles. So let's review just simply the parts of cars and what's involved. On this diagram here, we see a regular gasoline-powered car, and everybody's familiar with, we have a gasoline engine that would have a transmission. The battery here is very small, just a 12-volt battery, and you have fuel that you add at a service station. Now, if you wanted to make a plug-in hybrid, you have all of the parts that were in the previous slide. You still have a gasoline engine, you still have a place to put fuel, you need a fuel tank, but in addition, you have to add a lot more equipment. And so here we see there's a voltage converter, you need a controller for all the power electronics, there's an electric motor here, you have a different type of transmission than would normally be found. And most importantly, you have a very large battery pack. So as you can see from this, going to the hybrid option, even though it gives you some fuel and CO2 savings, it comes at quite a cost. The reason why hybrids are so popular now is that the biggest reason is the full electric vehicle, which we'll see on the next slide, really doesn't have the driving range that a hybrid has, or well, full electric can't take you as far as you want to go. So the hybrid has electric power, but it needs to rely on backup gasoline power so that you don't have to keep either going to a service station or filling up, charging your battery. And finally, we look at the all-electric car. This is a simpler design, except for the fact that for cars today, to get the kind of power you need quite a large battery pack. But in general, the moving parts and the number of parts is lower than even an internal combustion engine car, and certainly a lot lower than a hybrid. So again, the biggest problem with the electric cars, well, there are still many, but it's really the driving range. Most people would want to, especially if you take a long trip, you can't rely on an electric car. The other problem is the whole infrastructure. At least I know in the United States, you cannot drive and always count on having a charging station available to you if you travel across the country, whereas you can always find a diesel or gasoline station if you make such trips. So over time, the infrastructure will improve, and also the range and ability of full electric cars to go long distances, that will certainly improve as well. This next slide shows different types of hybrid configurations. It may seem a little confusing, but I show this only because you may see references to these P numbers. P is essentially the position in the vehicle where you have an electric motor. And this P system is really mostly designed for hybrids, but certainly in full electric vehicles, you also have to put the motor in a certain position. So with the P0, that's essentially a mild hybrid. And really all this motor does here, this is usually a pulley, a belt and pulley. All that motor does is essentially help you with starting your car. And it may also, well, you'll get regenerative braking in this type of design too. You can also have the P1 position, where you have a motor that's after your engine, and this can be used to give what we call that torque boost if you need some extra power. The P0 and P1 type of hybrids really don't need any different lubricants than what you would find in a regular gasoline vehicle now. So those are not of any real significance for the lubricant market. The time when you get into really looking at significant differences is when we get to P2 and higher designs. So this P2, you have the motor which is before the transmission, and you can use this motor to power the transmission, and you can actually turn your gasoline engine off at that point and strictly run on battery power. Similarly, you could put the motor after the transmission, and you still would have to select the gear, but essentially the motor at this position can then power the rest of the vehicle. There are designs where you have a motor in front of a rear axle, the differential. In fact, Teslas are designed like this, where they have an electric motor that's right before a differential gear set, and that essentially just powers the wheels. And really, at the end of the day, when you have an engine and a gearbox and all these things, you only really need to make the wheels turn, and that's an advantage of having the P4 configuration. And P5 takes it even a step further, where the motor may be actually essentially part of the wheel in the wheel hub. Sometimes if you have this design, you may have two motors so that you could independently vary the speeds on the two wheels. So let's look at the growth of electric vehicles. And in this slide here, which comes from the US EPA, you can see that each year there's been quite a dramatic growth and this is new electric vehicle sales. So to find the total vehicles on the market, you would add up all of the sales that have already occurred. And what you're seeing here looks like the beginning of an exponential trend, that the numbers are rising quite rapidly. And especially a country like China, they're making a big push on electric. Norway, which is here, is actually now about 2/3 of the country is already on electric or hybrid electric vehicles. So that's pretty remarkable. People still don't really know how fast the market will grow. And even if we look at the poll that we took at the beginning of this webinar, it was fairly equally split between people saying within 5 years or within 10 years, we would see a sizable number of electric vehicles. But even within those time frames, I haven't seen any credible predictions that said electric vehicles will be the dominant vehicle on the road. Certainly full electrics will not be dominant, but the hybrid electrics have a much better chance of gaining more market share. And again, largely due to the range that the vehicle can travel. This would be especially true for the commercial truck market. In order to power those large tractor trailer trucks on very long routes, it would be difficult to do that with just electric motors. They'll probably remain diesel powered for many years to come. But in any case, by 2030, the estimates in this graph, and I've got these estimates from many different sources, say that from 2 to 14% of the total global car fleet will be electric by 2030. So if we start seeing more electric vehicles, what will be the effect on engine oil consumption? So right now, because EVs are such a tiny fraction of the global population, there's not much impact that we're seeing now. In fact, in a region like Asia, I'm sure you're seeing, well, notwithstanding this current virus pandemic, but if we didn't have the virus, you would be seeing growth in lubricating oil sales. And if you look at what factors go into engine oil demand, the growth in world population and vehicle sales will certainly increase demand, and that's one of the reasons why Asia in particular is going to see growth in lubricant sales for years to come. The length of the drain interval will certainly influence sales, because the longer you can go without drain, the less lubricant will be sold. The proportion of the fleet that's hybrid electric will have an impact, because the hybrids will use some oil. If you remember the picture of the plug-in hybrid, it still has an internal combustion engine. In general, that engine is smaller. You don't need as large an engine. It will use less engine oil, and it will need a special designed engine oil. I can talk about that later. It doesn't have to be a custom oil, but certainly if you want optimum performance, customizing the engine oil will help. And then finally, the real factor that will drop lubricant sales is if we go to the full battery electric vehicles. Those vehicles use no engine oil, and that would have a serious impact on lubricant sale. And looking at where the fleet is expected to go by the year 2040, there are going to be 1.5 billion cars on the road. So there certainly would be a large market, and the only question will be what percent of those are battery electric. And certainly a good guess could be anything from 20 to 40% of the population at optimistic scenarios would be battery by that point. If we look at some projections, Klein predicts that total PCMO demand will drop by 1.2 million metric tons by 2040. And other analysts are saying about 1 or 2% loss of lubricant demand per year from this point in time. So hopefully that gives you some influence or understanding of the market. There are many people saying, oh, this will be the end of lubricants, and we are certainly nowhere near that scenario. And even by the year 2040, we don't expect that the lubricants business will be in big trouble, but certainly there will be some shakeouts of smaller producers, less efficient producers. Volumes will be dropping somewhat, and so you need to be a lot better marketer and a lot better informed in order to keep your business strong. So let's look at what types of fluids we'll need for hybrids and for the full or all electric vehicles. All of the vehicles out there, including the current internal combustion engines, they all need cooling fluids or coolants. And the hybrid gas engine still needs to be cooled. But now we have new factors. The batteries and motors, they need cooling. And certainly many car designs now are actually putting in separate cooling systems for both batteries and motors. This is obviously expensive, and people would prefer a better solution, and we'll talk about that in a little bit here. Greases will still be in demand, and certainly the electric motors will use grease, and you still have wheel bearings on the car, and as well as steering systems. Most of these greases will be, if not sealed for life, they'll have very, very long changes. That's one of the areas where I mentioned that if you don't have the factory fill for the person making a motor or for people making wheel bearings, there's probably not going to be a lot of demand in the automotive market for grease. All of the hybrid vehicles will need engine and transmission lubricants, and all of the hybrids in general will have the same types of transmissions that you see now in the market. If you have a hybrid vehicle, because you still have a gasoline engine connected, you will still have a choice of an automatic transmission, a dual clutch transmission, a continuously variable transmission, or even a manual transmission. And all of those will use the same types of lubricants we have now, with some exceptions that I'll get into a little bit later. Finally, if you had a full battery electric vehicle, you still need some type of a transmission. It's not really a full transmission like you'd find on a conventional vehicle. The motor speed can be varied over a continuous range, so you can use the motor speed to essentially change the wheel speed. But electric motors typically run at very high RPMs, often 10,000 RPMs or greater. And if you have an electric motor driving your vehicle, you don't want your wheels to be spinning at 10,000 RPM. You would be going probably 1,000 plus kilometers per hour in that scenario. So all of these vehicles need some type of what we would call a gear reduction, a gearbox where in general you only have one or two sets of gears, and it's a very simple reduction system. I'll show a picture later, and that will be needed with battery vehicles, and those boxes will need lubricant. So even though there's no electric motor, there will be a gearbox, and if the vehicle has a differential, you will also need some type of differential lubricant, which is this next bullet point here. So in general, the hybrid and the battery electric vehicles will use lubricants that are customized for that operation. And the biggest thing that people are going to be looking for in electric lubricants are whether or not the motor is actually in contact with the lubricant. So let me explain what that is here. So here's a picture of essentially a rear axle. There's a differential there, and it's connected to the two rear wheels on the vehicle. And everything that's in red, that's the lubricant. And in this type of design, you have an electric motor that's within a box that contains lubricant. And then you see the gears. So G1 is the first gear, then there's a G2 second gear. So if the motor is spinning at, say, 10,000 RPMs, this will go at 10,000, but now if you will reduce the speed with this. If this gear has twice as many teeth, you would take 10,000 down to 5,000. If this is turning at 5,000, if you had twice as many teeth, now you're down to 2,500 RPM. And that's how you actually get the speed down. In addition, you use the motor to vary the speed, but whatever motor speed you're at, you reduce it by a certain factor depending on what type of gears you have. So in this type of scenario, you want to have a lubricant that is compatible with electrical equipment. The alternate design is what we'd call a dry motor, and that's this picture, where the electric motor is actually a separate piece of equipment which is outside the gearbox. So all of this oil here doesn't really come into contact with the motor. So this makes things simpler. You can just use conventional lubricant in this type of design, but the reason why people like to have lubricant on the motor is that lubricant is a very good cooling fluid. So now let's look at performance needs if you had a wet gear set versus a dry one. So if the gearbox is wet, you really need to worry about what are the electrical properties of the lubricant. And we'll get into that in coming slides, but your electrical conductivity and what we call the dielectric breakdown voltage, those are important properties. And if you don't meet certain parameters with those properties, you could have some serious problems with your vehicle. We have a lot of new materials when a motor is introduced. You have a lot of copper that's exposed. You have insulation wire. You have other materials such as the magnets. We need a lot better aeration control because the motor is spinning at much higher RPM than a typical internal combustion engine would spin. And finally, heat removal is highly desired, so you want to customize the lubricant to get maximum heat removal. And finally, oxidation would tend to increase electrical conductivity. You make charged particles, molecules when you oxidize an oil, and that will increase the ability of the lubricant to conduct charge. You could get to a point where if you had a lot of oxidation, you may actually be able to short circuit the motor because you're conducting electricity through the oil. At this point in time, oxidation control doesn't seem to be an issue, but it really needs to be evaluated with more testing because we don't have enough experience yet to see how severe conditions would get, and with certain types of additives and base oils, how much oxidation could increase the conductivity. So speaking of conductivity, we'll look at now how we measure it and why it's important. So this picture here is just a little handheld meter that you just stick it in a jar of your lubricant, and it will measure conductivity. These pieces of apparatus are very commonly used because the fuel pipeline market and the service station market, everybody is concerned about conductivity of fuel. You don't want to start fires at your service station. So this is a well-known area of research and understanding, and now we're just applying it to lubricants. So essentially, you can measure it fairly easily. The units that are typically used are picosiemens per meter. Sometimes you might see per centimeter. And the interesting thing about conductivity is that you don't want it too high because you could short circuit your motor, but you also don't want it too low. Many people may think, oh, we should not have any conductivity. That would damage your motor. It would make your whole car a charged item. But really, you do want some amount of electrical conductivity because if you don't have conductivity, you can build up static charge. And certainly, many people have had this experience, in cold weather. If you're wearing a sweater and you touch a metal object, you may get a little shock. And that's, again, because of a buildup of static charge. So the nice thing about lubricants and oil in general is that it has a very low conductivity, but it's not so low that it doesn't allow any ionic movement. Lubes will conduct a little bit of electricity, and that's just enough to keep static charge from building up. In most situations, if you still have a poor design or a system where you're generating too much static, you may still see a problem, but in general, oil is very good at what we call charge dissipation. It will reduce the static buildup. And base oils are typically about 3 to 5 orders of magnitude. So that's quite a large number, in the 10,000 range, times less conductive than finished lubricants. And the main reason for this is that most of the conductivity you see in an oil comes from additives, because many of the additives have some type of charge. They're polar species. They may even be fully ionized, but in general, they do have some dipole moment or some charge separation in the molecule, and that helps basically conduct electricity through the oil. And there have been a lot of studies recently looking at designing additives so that you can affect the conductivity. And Afton recently published a paper where they looked at many different dispersant additives, and they had a range of anything from 300 to 6,100 picosiemens per meter for these different materials. So obviously, if you're designing a lubricant for an electric vehicle, you want to tend towards additives that don't conduct charge as much. So you'd like to be down at the 300 to 1,000 range instead of up at the 5,000 or 6,000 range. And part of that is also because even if you start off with a fresh oil that has very low conductivity, as the oil is in service, the conductivity generally increases, not only from the oxidation, which I mentioned, but temperature increases conductivity, and moisture will also increase conductivity. So for guidelines on where to design a lubricant, if you can make an oil that has more than 400 picosiemens per meter, you don't have much chance of a static discharge, but you want to keep the conductivity below 10,000 so that as the oil ages and it increases, you still don't get to a danger point on conducting too much charge through the oil. So right now, lubricants, as we mentioned, are good insulators. And if you're careful about your formula design, you can control the electrical properties and just make sure that if you have a motor in contact with a lubricant, you're not going to short circuit that motor. The other factor which is important, and many of you may be familiar with electrical transformers that are on the power lines. They're filled with an oil which is often called insulating oil or transformer oil. And one very common test in the industry, and I have a little picture here, it has two electrodes, and you keep increasing the voltage on these electrodes, and the electrodes are immersed in the lubricant, and you will reach a point when the voltage gets high enough that you cause a spark or a charge to pass between those two electrodes. Sort of like lightning in the sky. If you get a big enough buildup of a charge difference, you will eventually cause an electrical discharge, and this can be quite dangerous inside a vehicle. So this dielectric breakdown test will measure how much you can increase the voltage on your system before the oil essentially breaks down. And there's lots of ways to measure this. There's an IEC test as well as many ASTM methods. And the warning limits and recommended limits actually depend on what test you're using to measure it. Especially this ASTM D3300, that's a very different type of test. It uses an impulse voltage, and so instead of just increasing the voltage continuously and keeping it at a fixed level for a period of time, you actually cycle the voltage, and that has a very different breakdown limit. So oil typically breaks down in the range of 15 to 100, and that's million volts per meter. So it takes an awful lot of voltage per meter to cause a discharge. Now, obviously, if the distance between your charge surfaces is much smaller than a meter, which it would be in a vehicle, you don't need as many volts. You may be on the 1,000-volt range in a typical vehicle. But what you can see is that dry air will break down at 3 million volts. And so actually oil is a better insulator than air, which wouldn't seem obvious to many people, but it's really because of the dielectric breakdown potential. Air is a lot worse in that regard. Many people have a spec of 20 million volts per meter for what the oil, it has to be better than that, but it depends on many variables. And if you have moisture, other conducting contaminants, dissolved gases even can cause the voltage to decrease. So you have to be careful of those things. Right now, dielectric breakdown doesn't seem to be a problem. But certainly people will be monitoring it, and it is possible you may have a design that enhances this phenomenon, but right now we have not seen any major issues. Because of the high voltages you need, you typically wouldn't be able to generate that in a vehicle. Transformers are completely different because there you may be having step-down transformers where you start at very high voltages and you get it down to essentially a household voltage. And so there you have a lot more concern about dielectric breakdown. I mentioned materials compatibility, and the picture on this slide shows a motor, electric motor that's opened up, but this motor could be in contact with an oil, and you can see, a little hard to see, but those orange color things, that's actual copper wire. It's bare copper wire, and many times it will be coated with some type of polymeric material, and you'll have different insulating materials. That might be some paper type cellulose fibers, or you may have plastic insulation wire. All of those things need to be compatible with the lubricant. If you start dissolving your insulating wires, you could be in big trouble in an electric vehicle. So you need excellent protection against copper corrosion, and all of the additive companies are working on this, but Afton and Lubrizol in particular have published many papers already on new tests that they're developing, and also, very interestingly, Afton has shown that vapor phase corrosion can actually lead to field failure in a vehicle. So by vapor corrosion, what we mean is that the motor, the wires may not be in contact directly with the lubricant, but they may be in a space where lubricant vapor can reach the wires, and they found that there are actually differences on the amount of corrosion depending on whether it's in the vapor or the liquid phase. And there are new materials that have to be evaluated. Even the magnetic metals themselves need to be evaluated. This neodymium iron boride magnet, which I have down here, that's a very good magnet for motors, but it does corrode more easily than other types of magnetic materials, and so you've got to be careful if you're using this with lubricants. And at this point, we need to develop new test methods, because with new materials, you obviously need to look at different ways to evaluate them, and we need to get more field experience and field testing at this point. Now let's look at heat removal. Batteries and motors can generate a lot of heat, and if you're using high power, you can actually get up to 180 Celsius for short times. And so in order to both improve the motor efficiency and to improve the motor life, it's important to keep the motor cool. And I mentioned earlier that you could use an external cooling system like water or glycol in sort of a heat exchanger. But if you can use oil, that has some advantages. So you can either use air, oil, or water glycol cooling, and the oil is preferred when it's possible. So in order to use the oil, you've got to meet these electrical properties I've already discussed, but also we want to use oil that can remove heat rapidly. And in order to evaluate that, we've got a number that's been termed the Marantsev number. It's really a heat transfer coefficient, but it allows you to get a feeling for how much heat can be removed. And so the number is defined in this way, and this will be the only equation you see in this talk, where you've got the density raised to some power times thermal conductivity times heat capacity divided by viscosity, and essentially for any given oil at a certain temperature, the higher that number is, the more heat you are capable of removing. And so what you'll notice from this formula is that, and this should not be a surprise, if heat capacity, the CP, if that number goes up and if thermal conductivity goes up, you are removing more heat. That's what these numbers measure. So if your M number goes up, because these are high, you're removing more heat. But the very interesting thing is that it's inversely proportional to viscosity. The lower the viscosity, the better, the easier it is to remove heat. And so what tends to happen is many fluids, the thermal conductivity and heat capacity improve as viscosity increases, but you actually don't want viscosity to increase. You want it to decrease to make the cooling more efficient. So in a sense, you have a trade-off between these properties. Here's just an example of how different fluids can remove heat. And this very top line here, this is water. And the thermal conductivity of water is extremely high when you compare it to oils. And these numbers down here, these are oils. And so you can see that water is about 6 times better at conducting heat compared to oil. Glycerin or ethylene glycol, this is a standard coolant material, they're pretty good at removing heat, but certainly not as good as water. The big problem is, as we would all know, water is great for cooling, but you can't really put it in contact with electrical equipment. So if you want to use glycol or water cooling, you need to build essentially a heat exchange system. You need piping, you need a way to have a radiator to remove the excess heat, and that's expensive. The ability of your oil to remove heat. And there are definite differences between different oils. And in general, PAOs and synthetic esters have better thermal conductivity than the standard group 1, 2, or 3 base oils. So here's an example. PAO, it has a conductivity of 0.147. If you compared it to a standard mineral oil, it'd be 0.123. So the PAO is about 20% better at removing heat. And I think you'll find that most of the e-fluids that'll be developed in the future are going to use base oils that have better heat removal ability. And I mentioned before that there is a trade-off between getting higher thermal conductivity and low viscosity, that they move in opposite directions. And so far, from at least stuff that I've seen reported in the literature, it looks like viscosity is really the most important thing for good heat removal. But if you can optimize your conductivity and heat capacity, that definitely helps. But the lower viscosity is important. The big warning signal is that obviously if viscosity is too low, you may run into wear and fatigue problems on your equipment. And so you have to balance how low can you go with how much heat can you remove before you cause wear or fatigue. So now let's look at marketing fluids. There are a lot of companies now that have made announcements. I've found doing a lot of internet searching that many people are not publishing any data on their new products, not even really advertising them. And I think really part of the reason is at this point, the markets are very small, so fluid sales are small. Longer term, and I think many of you said this, in the introductory poll, it's good to have plans in place to think about what would you do if you needed to get involved with electric vehicle fluids. You certainly need to be prepared for hybrids and full electrics being more part of the whole vehicle population. And again, a lot of the action's going to be at the factory, not in the aftermarket. And so other than for a hybrid engine oil, most drain intervals will be very long. And this is just an example of some companies that have already announced e-fluids. Castrol, ExxonMobil, Fuchs, Petronas, Shell, Total, Valvoline. I've probably left the number off, but these are the ones that I've seen really making some type of marketing splash, but I have not seen a lot of data or performance information coming from these marketers. So to summarize, we're definitely trending towards more e-vehicles, and we will need customized lubricants. Right now, the market is small, and people differ on when it will be larger, but certainly the time is coming, and if nothing else, you should be prepared. You're not going to be in danger of missing out if you're not marketing now, but you want to be ahead of the curve and not behind the curve. We've talked about key properties that you need if you're making a custom lubricant, and the electrical conductivity is very important, as well as ability to remove heat. The interesting thing on this is that additive chemistry really has a big impact on conductivity of electricity, whereas removal of heat is much more determined by base stocks. So you definitely need a balance between the proper base fluids and the proper additive package in order to have the best performing electric vehicle lubricant. So that wraps it up for me, and I'm very happy to take your questions or comments at this point.
Thank you very much, Jack. For our audience, please send your questions through the Q&A that we have on the top left of your screen. Or if you would like, you can also raise your hands, and we will try to answer your question as much time as we have available. I don't see any questions that have been posted yet at this time, but let me ask you, Jack. You mentioned you're not seeing any data coming from the companies that have uh, advertised that they have EV fluids available. Um, for sure, there are no industry standards at this point. But OEM specifications usually are not published outside of their circle. Can you comment a little bit on what OEM specs there are for EV fluids?
Yeah, actually, that's a great question, Vicky, because um, the OEMs essentially started out by, as you know, I mean, everybody except Tesla was really more in the conventional vehicle market. So they had existing fluids already that they were using on their equipment. So most OEMs, when they started getting involved with hybrids or even with full battery vehicles, they tended to just try the lubricants they already had on hand. And in fact, those lubricants can work pretty well. Um, Certainly, a product like a Dexron 6 ATF, anything like the Nissan Matic S ATF, there are many excellent ATF products out there where they would function in an electric system, and they would be suitable. And that's what many people have done. And there are a few companies that are starting to make their own specs, but at this point, at least from what I can see, they're still feeling their way. And I'm on an SAE committee now where we are trying to develop some guidance for the industry on electric vehicle fluids. And, we're barely just getting started. We're looking at developing new test methods, looking at ranges of values that are important. And so I think it's one of these cases where the vehicles are out there and the lubricants will follow as time progresses. They'll get better and better as we get more informed about what's needed. But some OEMs certainly, I'm pretty sure, for example, BMW is working with one major lubricant supplier to custom develop for them. And, I wouldn't be surprised if other OEMs have programs already in place. But they're, as you said, they're not saying anything about it.
Yeah, I see a hand raised here, Nitin. Um, I'm going to turn on her microphone if she would like to ask a question. Um, okay. Well, um, Nitin, can you hear me? Okay, well, it says error in using microphone. Glenn, maybe you can assist her in her questions, and then we'll get on to other questions that come up, because I don't see how to fix this problem myself.
Yeah,
Going back to
I
S.
do see questions, Vicky, on the Q&A
Okay,
screen.
Yeah, now it's up. Okay. So, what about the typical viscosity for different EV applications today, and how low would it go in the future? This is a question from Liang.
Yes. Um, Today, I mentioned Dexron 6 ATF, and that's a good example of where viscosity would be today. That's a fluid of roughly 6 centistokes at 100 degrees C. And I also mentioned that in electric vehicles, if you have a full battery electric vehicle, you really only have a reduction gearbox, and it's a very simple setup. It's usually just a set of helical gears. It's not as difficult to lubricate as, say, a hypoid gear set would be. And so you can get by, and I would guess that even as low as 4 to 4.5 centistokes at 100, uh, you could probably get down to that lower range, but for now, people are probably in the 5 or 6 centistoke range.
Okay. Um, and this is different EV applications, right? So all kinds of fluids.
Yeah, I mean, I'm looking mostly at the reduction gearbox, but the engine lubricants would tend to also at 100. If you had a hybrid, you might be a little bit higher than that on centistokes, but you'd be maybe in the range of the 0W16, 0W20 type of oil. But that's not a full electric. That would be a hybrid.
Okay, we have another question from Chan Min Chang. The question is, will Group 5 or synthetic esters? Group 5 includes everything that's not included from Group 1 to 4. So that includes a lot of different synthetic products, right? Um, but she's referring, the question really refers to synthetic esters. Do they play a good role in EV car lubricant? Would it be any limitation with other types of oils?
Um, Certainly, esters, as I mentioned, they have good heat removal ability, um, and the esters can generally be tailored to conduct either more or less charge. So, I think you'll see definitely see esters as part of the lubricant. At this point, I don't see an ester being the main base fluid. One type of fluid, which was very interesting, that could play a big role, are what we would call the polyglycol fluids. Polyglycols also have extremely good heat reduction capacity, and they're not as electrically conducting. So you may see more of the glycol chemistry that's oil soluble. And some of those would be polymers. In fact, they would all basically be polymeric. So to get the low viscosity, you still have to add uh, probably something like a PAO or some base oil that's lower viscosity. So I think esters and glycols will play a role, but not the main role.
Okay, that sounds good. And you mentioned oil solubles because in the past there was incompatibility with water for PAG, but this is a new class of PAG that's been developed recently, correct?
Yeah, yeah.
Okay, for OEMs, how long would the warranties usually cover? This is a question from Pedro.
Yes. Oh boy, I can't really answer that. Everybody's different. I mean, most people now are giving quite long warranties on uh, engines, transmissions, and all parts. So a standard these days seems to be, um, well, I'm thinking in the U.S. in mileage, it would be 100,000. That would be 160,000 kilometers. That's getting to be a range where people would warrant equipment. Batteries are a different issue, but many people, uh, I would say certainly 5 years should be a battery warranty at this point, but I'm not certain what the actual market is doing. Uh, I'm, I know that in the early days of EVs, uh, most OEMs were saying they could get 8 years out of a battery, but whether they warranted for 8 years, that's a separate question.
Yeah, and you mentioned, I think in your chart, there's about right now to about 2 million electric vehicles globally,
Yeah,
right?
yeah.
So some of them probably have exceeded the 8-year warranty at this point. What's been the experience in the field that you've heard of?
Um, I haven't really heard of battery problems in particular with warranties. Um, and it's kind of interesting because many companies are trying to keep things as quiet as they can. Uh, a great example was Tesla. When Tesla first put out their electric vehicles, uh, they had a lot of differential failures. And the differential, normally, that's a device that could last easily 500,000 to 1,000,000 kilometers, and theirs were going out at maybe 100,000. And they ended up finding out, at least, well, again, everything was kept pretty hush hush. They eventually solved the problem, but uh, I think what was happening was the fluid viscosity was low, but because the electric motor, it can give a very high amount of torque uh, at very low RPMs. And so when the car is moving slow, it still gets full torque. That's completely different than a gasoline engine. Gasoline engine, if your RPMs go down, you lose torque. Electric motor, even at zero, when it starts up, it's at full torque. I think Tesla discovered that the torque at low speeds was too high, and current Teslas actually have a design where they limit the amount of torque that the motor can put out when the speed gets low. And I think that's to protect their differential. So I have heard of those issues. Um, I, there aren't really enough cars out there that I just haven't heard of much else that's at this point a major issue. The real big thing I think that's a problem for the batteries is not the lifetime, but the recycling. Trying to recycle a lithium car battery is really actually not something that's done now. And as your members probably know, I mean, lithium is getting in short supply because it's very heavily used for electric batteries. And so people who make lithium greases are seeing the price of lithium go up. But the big problem is we can't recycle batteries. So that's something that really needs to be addressed. And if we figure out a good way to recycle lithium, we'll actually improve the battery production and the battery life. Uh, Getting a decent life would be acceptable if you could just swap out a battery and it didn't cost that much. It's just like your car battery today. I've had car batteries that they may only last. I've had some that only lasted 3 years, and 3 to 5 years, and then you're basically getting a new battery. Uh, that's easy to do with a 12-volt battery. It's a whole different matter if you've got a whole power pack of like 300 to 400 volt batteries in there. That becomes very expensive. So they need to make that more replaceable at a lower cost.
Exactly. And actually, if you're getting 3 years, you're pretty lucky because I'm getting less.
Oh
So
boy.
so we have another question from Bernard. May I know the type of raw materials that will be used to produce the coolants, transmission fluids, and greases for electric vehicles?
Well, the coolants, if you're talking conventional coolants, they'll be the same materials that we have now because in those designs, a glycol coolant would not be in contact with a motor. It's sort of like your engine now on a gasoline car. Uh, the lubricant is cooling your engine, and then the lubricant is in indirect contact with the glycol, and that glycol removes heat, but it never really comes in direct contact. So those materials will stay the same, although people are trying to find better coolants for batteries, but really between water glycol type systems, that seems to be as good as people can get at this point. The base fluids and the fluids used for EV lubricants, my feeling is they're going to be either Group 4 PAO or some other type of synthetic. Given the long lifetime of most of these lubricants, you want to get the maximum possible oxidation stability and thermal stability, which would lead you to a synthetic. And they have the advantage of also having better thermal conductivity. So I think you'll see that. What will change are the choices of additives, but the additive companies are pretty smart about knowing what their materials can do. And instead of developing brand new materials, I think they will be picking and choosing what's in their portfolio now and taking the materials that already have good electrical and thermal properties and using those. But certainly there could be new advances, and there are always people looking. A great area that could help are like nanofluids, nanoparticles. You could develop possibly a lubricant chemistry with nano additives where the additives, if they had some type of little electrical charge, you could control how conductive the oil is. You could also possibly improve the heat transfer dramatically if you had some type of material that had a much better heat capacity and conductivity than oil. But when you put it in the oil, you don't impact the viscosity that much. So you may see some new things there. But in general, the materials we have now are suitable for using in electrics. The real difference will be just in how you rearrange those materials and how you formulate.
Sounds good. You mentioned you're involved with an SAE group that's looking into EV fluids. Can you tell us a little bit more about it?
Yeah, at this point, it's part of the SAE Technical Committee 3. So Tech Committee 3 handles driveline fluids, and they already have the draft of a specification, which I helped write. It will be SAE J3200. But at this point, the document is largely empty. We've got a number of different task forces, and each task force is responsible for a different area of performance. So in the talk I mentioned, you have electrical properties, you have material compatibility, you have oxidation, you have aeration, you have thermal conductivity. And so we have a task force for every one of those areas, and they're examining the test methods that are available. They're examining what OEMs need to make good fluids, but really everything's at an early stage. The group is hoping to have a document by next year. There's a good chance we would do it, but as you know, Vicky, you're a veteran of many ASTM and CEC and other committee meetings, and everybody's always very optimistic, but when you get down to getting it through a whole committee, sometimes it can take a longer time.
Yes, 20 years.
Yeah.
So if someone would like to get involved in Technical Committee 3, what do they have to do?
Well, the first thing is you need to be a member of SAE, and then you just request to be added to the Technical Committee 3 roster. And if you're on Tech Committee 3, even just as a non-voting member, and we have mailing list members, I mean, you will get minutes from meetings, you will get informed, you'll get to see the annual meeting, notices and minutes. But yeah, it's in the grand scheme, SAE is always going to be a little bit behind what's really happening, because the additive companies, base oil manufacturers, and OEMs only want to share so much information. They they have competitive advantages and they have some proprietary knowledge, and they're not going to share that at this point. But they certainly are willing to share some common things just to help the market in general, and that's what you'll see come out of SAE.
Okay, that sounds good. We have a question from Michael Young. How about battery cooling? Is this same concept for liquid cooling in battery? Since glycol cannot conduct battery or engine, but useful. Glycol cooling or oil immersion cooling, which one will adopt more in marketing?
Well, I think the batteries are going to use glycol, but they will use glycol, at least from what I've seen, that is still separated from the actual battery material. So what you'll see in batteries, and this is there now. Tesla is a good example. Tesla has, I think, something like 9,000 individual battery cells that are all lined up and packaged together to make a very large battery. Uh, they'll have row after row of these battery packs, and in between the rows, you'll have maybe a little aluminum frame and a channel that will conduct the coolant. So the coolant will not touch the battery. The heat gets conducted through the metal pipe, and that's what you'll probably see. Now, certainly, people could probably come up with ways to cool a battery directly by immersing it in a fluid, but I'm not enough of a battery expert to know where they are on those developments.
Okay, I don't see any more questions unless anyone raises their hand. Uh, maybe we can. Bernie, you have your hand raised. Do you have a question for Jack? I'm actually turning on her microphone. Bernie,
Yes.
do you have a
Can
question for Jack?
yes, I have.
Yes, but please go ahead.
Okay. I was going to ask because following up from earlier where he said that the recycling of battery is difficult at this point. Is recycling of battery going to be the reason why it would take like 10 years for the EVs to be developed? Because I understand that recycling cannot be done by humans alone because of the toxic waste, maybe on the cobalt and the lithium. And I understand that it will have to be robots to do the recycling. Is this the reason why EV would take like 10 to 15 years to develop?
Um, no, I don't believe so. That recycling would definitely help, but it's not essential at this point. But if we don't recycle, that means we have to mine more lithium. And ever since the battery market increased, more and more people are starting to open mines to find lithium. So even though there was a period just 1 or 2 years ago when lithium prices went very high, they've come back down again because people have figured out ways to get more lithium out of the ground. Obviously, it's like oil where you can't just keep mining lithium forever. There will be a point when you run out of lithium. And the thing that recycling would help us do, it would help us lower the cost of a battery. Right now, electric vehicles do suffer from high cost. So that's an impediment. But and for most people, I would say that's the major impediment. But the other impediments are the lack of charging infrastructure and the lack of a long range for driving. Those are issues that are also very important, and it will take a long time to solve those issues.
Yeah, I understand because from 2017, I understand that there's already about 250,000 waste batteries that is being dumped because they're unable to recycle this.
Yeah, it's a shame. I mean, I almost couldn't believe it when I was reading my chemical magazines that that we really can't recycle lithium. You would think that people would have considered that from the beginning.
Yeah. Okay. Thank you. So it's going to be waste. I mean, disposal of batteries is also going to be a problem. Then, would that be correct?
Oh, yes, yes, it will be. But I believe, I mean, people are working very actively on recycling now. So I'm optimistic that within a few years, they will have ways to recycle. And a lot of it will have to do with how the batteries are manufactured. That if you make something knowing ahead of time that you're going to have to take it apart at the end, you would design it in a way to make it easier to recycle.
Okay. Thank you, Jack. That was very helpful. Thank you.
You're
Thank,
welcome.
thank you, Bernie. Jack, I don't see any more hands raised. Would you like to give our audience a last message, maybe something that you wanted them to take away? The most important aspect of electric vehicles and what our role is as lubricant manufacturers, perhaps?
Yeah, I mean, I think what I would tell people is that, and we saw this from the poll at the beginning, 73%, of your audience today either has no involvement or just studying what to do now. And my message is, don't worry at this point. I think in webinars like this and what other work that Almu does, you just need to keep informed of trends in the industry, and it'll be up to you to decide when to take some action. But getting educated ahead of time and then planning what you think the future scenarios will be is important. I believe we have time before the market gets really large and gets significant. And so every one of your audience members now, you have the time to study more. Hopefully you learned a little today about what is different about an electric vehicle lubricant. Many things are the same, but you see the differences. And the message I have is that what we know now about electric vehicle fluids is there's really nothing that we don't that we don't have control over at this point. I mean, it's not an unsolvable problem by any means. In fact, we've basically solved a lot of the problems. At this point, it's really about optimizing and making things better. So, yeah, we certainly, there will be opportunity there, but this is more just to help you be informed and to stay ahead, of your competitors, and just be prepared for what will happen in the future.
Well, thank you so much, Jack, for that message. And at Almo, obviously, one of the things that we try to do is actively tell people what's happening in the marketplace, not only in Asia, but globally. And before we go, a big thank you to Jack. This is the third and the last webinar that Jack will be holding for Almu. Our next webinar is going to be in August, and our topic will be on engine coolants. And our presenter will be Mr. Amol Chori from Arteca. And the date of that webinar is August 25 from 10 to 11 a.m. Singapore time. And at the moment, we have another webinar planned for October, and that's going to be on October 13. And that will be industrial gear oils, and that will be presented by Lim Chun Noi from Afton Chemical. So thank you very much, everyone, for hanging in there and for sending us your questions. And if you have any more questions, please don't hesitate to contact our secretariat, and we'll try to get them answered for you. Thank you, everyone, and have a great day. Bye.